Welcome back to our course on scanning electron ion probe microscopy in material characterization. In last couple of few lectures, we have been discussing on the scanning probe microscopy, and we began with scanning tunneling microscopy. We have discussed on how the tip is fabricated for scanning tunneling microscopy by electrochemical etching, and then we have started discussing on piezoelectric scanner, the basics of piezoelectricity. Today we will continue with that, essentially how the piezoelectric tube works in STM. In the last class, I have discussed on piezoelectric plate, but actually in the scanning tunneling microscope we use piezoelectric tube, and how it works and what is the limitation of the piezoelectric element we will discuss in today's lecture. In the STM, we want the tube or piezoelectric scanner to move in all three directions, x, y and z direction, with an accuracy h small h 0.1 angstrom, and therefore, this piezoelectric scanner should allow us to move the tip in every direction x, y, z direction as precisely as possible. The piezoelectric tube has the advantage of having high piezoelectric constant and having high resonant frequency, and this tube consists of a piezoelectric ceramic that you see here, piezoelectric ceramics, and the metal plates. Metal plates are there outside and also inside. Inside we have a metal plate, this is red color is metal plate, and we have metal plate, 4 quadrants are there, 4 quadrants are there in the outer side, and in inner side we have again metal. So, this is what the tube made up, particularly with a material called PZT or lead zirconia titanate, and the motion in the z direction or nothing but longitudinal direction can be achieved by applying the voltage between the inner and outer electrodes, metal electrodes, because this piezoelectric material is a ceramic material which is insulating in nature. Therefore, we need to have a metal electrode to apply the voltage. In the longitudinal direction, we can change the z moment. Similarly, in the deflection in the x y direction or nothing but transverse direction, we can move the tubes in the x y direction. And here, as you see, the deflection in the x y direction can be induced by putting opposite polarity of the voltage to the outside electrons, and in the one side the tube is shrinking and in other side it is expanding. So, this is a bipolar operation of the tube where voltage of opposite polarity is given to the opposite electrodes, and this vertical displacement del L can be calculated with a piezo constant, as we know, let del Z by del V is nothing but it is del L and del V, which is equal to T31 L upon H, where L is the length of the tube and H is the thickness of the tube wall. H is the thickness of the tube wall. So, for the vertical displacement we can calculate by using this equation. Similarly, in the transverse direction it can be also calculated in the transverse direction. This is for longitudinal direction, and for transverse or lateral moment, for lateral displacement, that is del x by del v is nothing but d31 L square by dm h. Here dm is the mean diameter of the tube, mean diameter of the tube, and rest of the parameters are same. Here as the tube is bending, we assume that there is a circular arc, it follows a circular arc. Using that assumption, one can calculate the lateral moments of the tube using this equation. But in the calculation of the lateral moments of the tube, it has not taken into consideration of the stress formed in the metal electrodes. As the tube bend, there will not be a uniform stress with the metal electrode. So, if we consider the non-uniform stress on the metal electrodes, considering the non-uniform stress in the metal electrode, one can calculate this lateral displacement del x by del v is equal to 2 root 2 upon pi, then it will be again d 3 1, then L square by d m h. So, using this equation, one can find the moments of the piezoelectric scanner either in the vertical direction or in the lateral direction, and how much potential therefore needed to move the piezoelectric scanner upward or in the sideways. And this equation is for the bipolar operation, where voltage one side a negative voltage, another side positive voltage is applied. So, to this electrode left side one side electron in the x side it is negative and other side is positive. Typically if we consider for a commercial piezoelectric tube with a trade name, let us say trade name of PJT 5A, then for that the typical length follows, length is around 25.4 mm and mean diameter is around 5.84 mm and the wall thickness of the tube or H is around 0.51 mm. So, using these parameters or using these factors, one can find the piezo coefficient. It will produce a piezo coefficient in the x and y direction of around 725 angstrom. One can do MOP per voltage per volt. Similarly, for z direction, it will be around 90 angstrom per volt. It will be around 90 angstrom per volt. So, one can design the tube using suitable length, wall thickness to see how much piezoelectric coefficient can be achieved per volt. This is what actually used in our STM as a piezoelectric scanner for the moments of the tip in 3 orthogonal direction x, y, z. But actually on this piezoelectric tube, we have the tungsten or platinum tip is fixed, which interact with the specimen, because in STM both our tip and this specimen has to be conducting. So, this piezoelectric tube will only make the moment of the tip upward, downward or in the sideway x y direction, but it is not going to measure the current or tunneling current that we are interested to measure using this scanning tunneling microscope. So, a tip is tungsten or platinum iridium tip is fixed on the on this tubular piezo scanner to measure the current. So, normally in this tip is placed at a distant L tip above the center of the piezo tube. So, thus it can provide an additional deflection del x tip. As it provide additional deflection, we can find that additional deflection del x tip is equal to L tip sin alpha. We can write it sin alpha because it is in bending motion. So, alpha is the bending angle, here alpha is the bending angle, and which is nothing but it is quite small. Therefore, we can write L tip alpha, and which is nothing but is equal to L tip 2 del L by dm, and which is equal to L tip for root over 2 divided by pi d31 L del V dmh. So, I am not going on detailed derivation of this equation, directly putting all these here, how the del x tip is calculated. This is a additional deflection when we put on the piezoelectric scanner. So, but then this is the additional deflection. If we total deflection we see, that means the deflection due to piezoelectric scanner and also the deflection due to the tip by that then we have to combine. By combining the x deflection of the piezo tube, the total piezo constant for horizontal deflection will be del x total divided by del V is equal to del x due to piezoelectric tube scanner plus del x tip, this is additional deflection, then del V. By putting these two equations, we can get 2 root 2 upon pi d31 L piezo and divided by dmh L piezo plus 2 L tip. Here L piezo is the length of the piezoelectric scanner and L tip is the distance above the center of the piezo tube after putting the tip. So, that is that L tip. So, in this way one can find the total horizontal deflection that will be occurring in a STM using a tubular piezoelectric scanner. This is what about the piezoelectric scanner which is used in our STM for moving the tip in different direction on the specimen. Now, we will come to discuss on the limitation of piezoelectric actuators or piezoelectric scanner. There are 4 major limitations. First is non-linearity, then hysteresis, grip and thermal drifts. We will go one by one. Non-linearity. Here non-linearity means that deformation or displacement of the piezoelectric material or piezoelectric tube is not uniform in a large range of potential. It is not that we can apply any potential, keep on applying potential and it will keep on giving more and more displacement. There is a linear range, there is a range of the potential where it shows linear increase in the displacement. Afterward, it gets saturated. As you see here in this plot, del z is increasing up to a potential here, after that it is no more linear. So, in the STM we can only use this range of potential where it shows the linear behavior. We cannot use a potential above. Therefore, there is a limitations to a piezoelectric scanner up to what length it will show the displacement. We cannot therefore do the scanning of the sample in a micrometer scale, because piezoelectric scanner will not allow us to show the displacement or move to any length on the specimen. That is one of the reason why large area scanning is not possible by STM. This is about non-linearity. Then we have another problem is hysteresis. So, hysteresis occurs when the displacement, when we increase the potential, then displacement del z increases, and when we decrease the potential, then it gets contracted, it gets extended and contracted. When they do not follow the same path, we say it is hysteresis. And there are two main contributions that led to the strain or displacement in the piezoelectric ceramic, and that is in presence of electric field or applying the voltage. One is intrinsic effect. Intrinsic effect occurs due to displacement of ion inside the crystal, like in the PZT we have titanium atom, which was displaced upward from the center in the vertical position, that the examples I had given. That is the intrinsic effect, which is due to the displacement of the ions. And the second is extrinsic effect, which is due to orientation of the ferroelectric domains. Most of the piezoelectric materials also show ferroelectric characteristic, particularly the PZT, which is used as a piezoelectric ceramic in the STM, that also show ferroelectric behavior. Ferroelectric is nothing but a permanent electric dipole, presence of permanent electric dipole even in the absence of the electric field, or even in the absence of outside voltage applied to it. So, as it has ferroelectric characteristic or behavior, it has a ferroelectric domains, and they will reorient it when we apply the voltage or potential, and we will see here how those reorientations occurs. So, inside the ferroelectric inside the crystal ferroelectric inside a ceramic material which is soft ferroelectric behavior, there are domains, ferroelectric domains which have different orientation. Particularly, for example, in this case PZT, titanium ion in the crystal lattice can move in 6 different directions, and therefore, domains with 6 different orientation exist in the crystal lattice. So, now if the domains, these domains have internal electric field, if the internal electric field of the domains align along or parallel to the applied electric field, if the internal electric field of the domains is parallel to the applied electric field, then that will be in the lower energy states. If the inner field of those domains is anti-parallel to the applied field, then they will be in the higher energy states. So, now these domains would like to stay in the lower energy states, and therefore, they would like to reorient themselves in parallel to the applied field. However, there is a barrier, they have to cross that energetic barrier to go from higher energy states to lower energy states, and during that when they cross one when they want to cross that energetic barrier, or in order to cross that energetic barrier, those domains will experience the domains will experience a certain requirements of the field, and in order to do that, what will happen that the history of these materials will play an important role, like how these materials previously been applied with a voltage, and therefore, how they will behave for their reorientation of those in our electric field. For example, let us say here at position 1 here we have 6 domains, all are orienting in the same direction of the applied field. Therefore, displacement is maximum. Here field is positive, displacement is high, and this is the saturation polarization. All domains align in the applied field, that's low energy states with a maximum strain. And when we go from 1 to 2, by decreasing the field, or when field is reduced, applied voltage is reduced to 0, then most of these domains again align with the outside with the outer field, but there is one domains which is reoriented, and this states is what the remnant polarization still exists, thus having remnant strain. So, the remnant strain or remnant polarization is the polarization or strain at 0 applied voltage. And when we reverse the potential, when we go towards negative potential, what we again see, there is again reorientation of those domains. When this happens, we come to a stage where there is almost no net polarization, where 3 are downwards and 3 are upward, no net polarization. And then again further increasing the voltage in the opposite direction, that is negative voltage, we find that all are in the antiparallel, and therefore, the displacement. So, what we see they and this when these domains go from low energy states to high energy states, they have to overcome the energy barrier, and that depends on the history of the material system, and how that materials undergo changes before we apply this particular voltage cycle. And due to this hysteresis, the extension of the piezoelectric scanner or piezoelectric element do not only depends or does not only depends on the applied field, but also the history or the specific states of this domain structure. And now, when they come from 4, when we reverse the potential, the way we gone, when we decrease again we increase the potential from negative to positive, those will not follow the same path it has come. They will follow, they are following a opposite different path, 4 to 5, then 6, then 1. So, this is due to this is called the hysteresis behavior, and what it is showing is a butterfly type of curve. It is showing a butterfly type of curve, and between 1 to 2, this is between 1 to 2 when the orientation changes, and the change in these cases, the displacement is due to the intrinsic effect. Between 1 to 2, this is a unipolar operation, that is in the only positive direction, that is positive direction. It is the unipolar operation where the orientation changes from one to another, and displacement changes here, that is due to intrinsic effect between 1 to 2. Between 1 to 2, the strain is mainly induced by intrinsic effect, and in the 3, net polarization of the domains is 0. So, in actual scanning probe microscopy, we would, it should not be reached to 0, otherwise it will be complete depolarization, and in the 4th maximum polarization. So, the working range of the unipolar operation is between 1 to 2, and for the bipolar operation that we have seen in our piezoelectric tube, that is what used in STM, and for bipolar operation we should not come and reach the 3, but before than that. So, so operation has to be done up to a potential below the 3, because at 3 there is a complete depolarization of the system. So, this is this hysteresis, because they do not follow the same path and so or so a butterfly type of curve, the STM tip is not scanned from left to right and right to left, left to right or left to right. We do not scan in the STM operation due to this hysteresis behavior, and we will see, and due to the hysteresis behavior also we cannot use very high potential and make the piezoelectric scanner to move a larger distance. So, this is what you see, a type of piezoelectric curve. The two effects are observed in this voltage sweep. One is the displacement is different for increasing and decreasing voltage. As we see, as we increase the voltage, the displacement, let us say displacement is here up to displacement up to a certain point here, and then when we are decreasing there is another displacement. This is one thing we see, and second thing is the hysteresis increases for larger voltage amplitude. As we go to a larger voltage range, then this amplitude hysteresis is increasing, this green curve. And due to the hysteresis, piezo constant ratio of the displacement and voltage is not constant anymore. This is due to, and rather depends on the applied voltage and on the history of the system which voltage applied before. So, this is the important factor that gives the hysteresis to the system. The average piezo constant for the smallest and largest voltage sweep differ by here. This is the average piezo constant, this green dash line and the another pink color dash line, and due to this, if we go for larger voltage applications to the piezoelectric scanner, then image distortion would occur. And in order to use the larger voltage, we need for to scan the larger area, and therefore, we cannot scan larger area of the specimen using the STM. Then another limitation is the creep. It is the delay in the response of piezoelectric scanner to sudden change of the electric field. As you have seen in our hysteresis, there is a reorientation of the domain, as those reorientation of domain needs time. So, therefore, those are time dependent function, because those are energetic phenomena, they have to come cross the energetic barrier from one orientation to another orientation, as they are time dependent. So, therefore, this is slow process, and when we change the voltage, it will not suddenly jump to that displacement quickly, it takes time, and therefore, as you see here, when we are giving the voltage V, our del Z is not exactly following the same path. Similarly, when we are increasing a voltage V here, you see how the displacement along the x direction, and this also one of the limitation. In the absence of the creep, it would exactly go to the same position, the displacement will occur same position, and this is another reason why, like for example, if we want to move the piezoelectric scanner towards the x direction, we apply the positive potential, and that tip starts to moving towards positive direction, and when we again starts bringing the piezoelectric scanner in opposite direction in the negative scale, still our tip will be moving towards right. This happens, and that is one of the main reason in the STM we scan from left to right like that, instead of going left to right, right to left like this. Other another is thermal effects. Thermal drifts also occur. Thermal drifts also cause some kind of distortion that should be reduced. So, what we have seen in this lecture, that in this lecture and also previous lecture, that deformation of the material upon applying the voltage is due to the piezoelectric effect. That is what I told in the introduction while discussing about the basic of the piezoelectric effect. And the piezo constant describes the sensitivity of the piezoelectric actuator in a unit angstrom per volt, that unit angstrom per volt, that is either del x by del v or del z by del v. Similarly, the piezo constant is independent of the thickness of the plate when longitudinal piezo effect is introduced, that we have discussed in our last lecture. And while for transverse piezo effect, the piezo constant can be varied by tuning the dimension. Piezo it is like x by z, this for transverse effect proportional to. So, by increasing the x and decreasing the z, we can increase the transverse piezo effect, piezo effect, but there are also limitations if we increase the x and we decrease the z. A tubular piezo element is used as a scanner in STM. The non-linearity, hysteresis, creep are the some issues with piezoelectric actuator, due to which SPM is not suitable tool to examine larger area or nothing but in micrometer range. Another reason, hysteresis and creep are also the reason why in SPM two successive line scans are not scanned in the opposite direction. They are not scanned, first scan from left to right and the second scan is from right to left to right, right to left is not done, but they always TP scan from left to right and then again left to right. In this way we scan the specimen. These are the references. Thank you.